Hello everyone, my name is Shah from Center for Advanced Imaging, Brisbane, and I'm going to talk about the SAR reduction method for FLAIR at 7 Tesla. I have no financial interest to declare, so I want to start with the basics of FLAIR sequence. In FLAIR, we start with an inversion. We wait for a certain amount of time, which is inversion time, and then we excite the spins, we run the readout module, fill the K space, and form the image. But how does FLAIR uses the concept of inversion in brain imaging? In brain, we have three different tissues: white matter, gray matter, and CSF. And if we choose the inversion time of the FLAIR sequence at the null time of CSF, and we excite the spins here, we will end up with this image where we don't have any signal from CSF, but we have a good contrast between white matter and gray matter. So CSF suppression is a key feature of FLAIR. And how can it help us? It helps us in detecting many diseases related to the brain. And multiple sclerosis is one among many applications. And you can see that CSF suppression in FLAIR can help us to visualize these plaques. But do we benefit from 7 Tesla if we implement FLAIR at ultra high field? Of course, yes. These are 3 different images and 3 different field strength, and you can obviously see that at 7 Tesla we get a better SNR for FLAIR. But is it easy to implement FLAIR at 7 Tesla? No. If you have a 7 Tesla in your center, and if you go to 7 Tesla and run this FLAIR sequence and get an image, you will get this image. You have a better SNR. The SNR is improved, but it has low image quality, and you can see significant signal drops at the temporal lobes. But why is that? It's because B1 inhomogeneity, the most common challenge of ultra-high field imaging. So if you go to ultra-high field, the wavelength of the pulse decreases and it becomes comparable to the dimension of the tissue, head, and it causes the formation of standing waves, and it causes non-uniform transmission of the RF pulse. B1 map is the best tool to visualize the inhomogeneity. And I have provided you with 3 different slices of the B1 map, and you can see at the temporal lobes you have less than enough power. At the center you have more than enough power, and this means non-uniform transmission of the RF pulse, means non-uniform inversion, means non-uniform CSF suppression, and means low image quality. So among different possible solutions of solving the inhomogeneity problem, like dielectric pads, parallel transmission, and adiabatic pulse, I chose adiabatic pulse because it didn't need any additional hardware. And among the plethora of adiabatic pulses, I chose TR foci. You can see the waveform of the TR foci here. And in this slide, I'm going to show you why TR foci is robust to B1 inhomogeneity. Here you can see the slice profile, and I'm going to walk you through different amplitudes from 0 to 600, and you keep watching the slice profile here. So if I start from the low slice profiles, and you can see the slice low amplitudes, you can see the slice profile will change. But as soon as I pass the adiabatic condition here, you can see after passing the adiabatic condition, it doesn't matter how I change the power of the pulse. The slice profile is the same. So it doesn't matter how much is the B1, the slice profile is the same. And this is a significant robustness towards B1 inhomogeneity. So with adiabatic pulse, which is TR foci here, I solve the problem of inhomogeneity, but at a cost of SAR. This is because the inhomogeneity problem is not the same for all slices, and it overdrives the pulse. So for the inferior slices, the inhomogeneity problem is so severe, so I have to increase the power of the pulse to make sure that the adiabatic condition is satisfied. But for the superior slices, the inhomogeneity problem is not that much severe, so that power is too much. So if we can adapt the power of the pulse slice by slice, we can solve this problem, and we can mitigate the B1 inhomogeneity while reducing the SAR. But for that, we need prior information. We need B1 map. This is the most straightforward method of getting the B1 map. There are many sequences. SAR is one of them, but it takes up to 2 minutes and it disrupts the clinical workflow. And we were thinking that, is there any method that we can circumvent this step, we noticed that in the localizer scan, there is B1 information because we could see the B1 inhomogeneity artifact in the localizer itself. So we were thinking that is there any tool that can predict the B1 map that we want from the localizer? And the answer is yes, CNN, the convolutional neural network. So we used the unit architecture of the convolutional neural network, and we trained the model using 26,000 pairs of patches of localizer and B1 map. So the model could predict B1 map from the localizer. And this is the result of the generalization stage of the model. We fit an unseen data into the model. This is what we want. This is the prior information that we need, but it takes 2 minutes, and we acquired that using the SAR range. But this one is the prediction of the prior information, which didn't cost us neither SAR-wise nor time-wise. And here is the prediction, is an error, relative error map of the prediction. So we saw that we have 5% of error across the brain, and we want to investigate if this amount of error is would be problematic or not. So we established our SAR reduction workflow. So we started with the SAR range. We acquired the prior information that we wanted. We resliced the slices in the, we resliced that in the FLAIR acquisition slices. We used simulation to exclude the pixels where the B1 is above alveolar threshold. Then we calculate the scale factors, and we acquired the FLAIR in 2 different modes. In the non-scaled mode, the power of the pulse is the same for all slices. But for the scaled mode, we adapted the power of the pulse slice by slice using the scale factor that we calculated based on the measured prior information. Now we want to see if CNN can help us here to get rid of this measurement step. We started with this localizer, we fed into the model, we predicted the prior information, and then we did the same thing, and we acquired another scaled mode of the FLAIR. This time, we use the scale factors that are calculated based on the predicted prior information. And in the result, you can see that the scale factors are following the same trend. It means that the accuracy of the prediction was good enough, and it didn't affect our application in vivo. So for the purpose of scale factor calculation, the prediction of the model was accurate enough. And with these scale factors, we could save up this amount of energy. And these are the FLAIR images in 3 different modes. Here is the non-scaled mode, where the pulse is overdriven and the power of the pulse is same for all the slices. And you can see that we exceed by 40% in the SAR, but for the scaled modes, either for the scale factors that are calculated based on the measured prior information or the predicted prior information, you can see with either of the scaled modes, we can save 27% in time, 43% in SAR, and hopefully you can't tell which one is which one. It means that we reduce the SAR, we reduce the time without touching image quality.